Dear students, so far we have discussed the interaction of heavy charged particles and fast electrons with matter. Today we will discuss the interaction of electromagnetic radiations with matter. So electromagnetic radiations essentially comprise of gamma rays and X-rays. So gamma rays, as you know already, appear from the de-excitation of the excited nuclei, whereas the X-rays come from de-excitation of excited atoms. In addition to this discrete gamma rays from the decay of excited nuclei, we also have Bremsstrahlung, which we discussed during the interaction of beta particles with matter. And this Bremsstrahlung essentially have a continuous spectrum starting from 0 to the endpoint energy of beta, or even for that matter, a fast electron. Now, the Bremsstrahlung, you know already that when an accelerated particle is moving, if it is accelerated in the vicinity of a nucleus, then it emits a Bremsstrahlung radiation. So all of them, all interactions, all the types of radiation, gamma rays, X-rays, and Bremsstrahlung, they are electromagnetic radiations, and the interactions with matter are same. So we'll call them mostly in terms of gamma rays. So gamma rays predominantly interact by three modes: the photoelectric effect, the Compton scattering, and pair production. So the major deposition of energy in the gamma ray detector, which essentially you will see how they manifest in the gamma ray spectrum, comprises of these three processes. And since the gamma rays are photons, they will not cause the ionization directly in the medium, but by these three processes, photoelectric effect, Compton scattering, and pair production, ultimately the net result is ionization and excitation. By secondary means, they will produce electrons, which in turn will cause ionizations. So there is no primary ionization in the interaction of these gamma photons with the matter. It is mostly by secondary ionization. Whatever electrons are produced, as we will discuss very soon, in these three processes, they will cause ionization, and therefore we get the secondary ionization. Another important point is that since the gamma rays are photons, their specific ionization is very small compared to that of electrons. So their ranges, as I discussed, their ranges are very high. So about 1/10 to 1/100th of the electrons, they will cause very less specific ionization. Means the per unit thickness in the medium, how many ion pairs they can produce, that is called as the specific ionization, number of ion pairs produced per unit thickness. So that is very small, and that's why the gamma rays, or even the X-ray, Bremsstrahlung, they all travel a long distance in any material. But then we know, we will discuss very soon, that it's the IZ materials which can stop the gamma rays effectively, and so they are the ones which are used to stop these gamma rays. So let us discuss the main three processes. What is the mechanism? What are the manifestations in the gamma ray spectrum? The photoelectric effect, you all know from the Einstein's theory of photoelectric effect. Then when the photon interacts with an atom as a whole, so it is not with the electron, but it is there with the absorbed atom as a whole, then in the vicinity of the atom, the photon disappears. It is completely absorbed. So it can also be called as photoelectric absorption. And so the atom gets excited, and the excited atom loses its energy by emission of electron. In the case of photoelectric effect, probability is maximum for emission of the highest bound electron. So that means the K shell electron has highest probability of emission, provided the energy of photon is more than the binding energy of that particular electron. So essentially the effect of photoelectric effect is to release one electron from the atom, and the kinetic energy of the electron will be the initial energy of the photon minus the binding energy of the electron in that shell. So this is the schematically shown here. The incident photon comes, it is absorbed by the atom as a whole. So the important point is that the momentum of the photon, say photon has a momentum E by C, that is balanced, that is, it has to be conserved, and that is conserved by the atom as a whole. So all the momentum is taken up by the atom as a whole, and so the excited atom that emits the electron from the K shell or L shell depending upon its energy. So it is important for the conservation of momentum that the electron which is closest to the nucleus is participating in the photoelectric effect. And the photon, the electron that is produced, we will be calling as the photoelectron. The photoelectron energy, as you can see, if we have a 1 MeV gamma ray and binding energy of electron may be about few tens of electron keV, then the electron will be coming out with a very high energy, and so that electron can cause subsequent ionization in the medium. So this process of photoelectric effect essentially leads to the full energy deposition of the gamma. The gamma ray is lost. So all energy of gamma ray photon is deposited in the material in form of electron, and the electron will stop now in the medium. So essentially it will cause ionization. The photoelectric effect is the predominant mode of interaction at the low energy of photon. As we will very soon see, the dependence of the cross-section for this process, the energy of the photon, and the Z of the absorber material. And as I mentioned that for this momentum conservation, the shell closest to the nucleus is excited, so that the electron coming from the K shell has the highest probability. So the highest probability of absorbing the photon is for most tightly bound electron, that is K shell. So if the energy of the photon is more than the K shell binding energy, then it is the predominantly K shell electron that is emitted. Now, so what essentially has happened, there is a hole in the K shell, electron has been emitted. So the post-photoelectric effect, what happens? There is a hole in the K shell. Then the electrons in the higher shells will jump down to the lower shell, and in the process you will see the X-rays being emitted. And subsequently, this when it comes to the valence electrons, even this instead of X-ray emission, the OZ electrons may also be emitted. So as a result of the photoelectric effect, we have photoelectrons, X-rays, and OZ electrons being emitted, and all these X-rays again will cause photoelectric effect. Their energies are much smaller, so they will be having much smaller ranges, and so all of them ultimately deposit energy in the medium, and you get the full energy deposition in the substrate. So the probability of the photoelectric effect depends heavily upon the Z of the absorber, Z to the power n, where a Z is the absorber atomic number, and this n value is quite high, 4 to 5. Whereas it depends upon the energy of the gamma ray in inverse way, e to the power 3.5. So these dependencies have come from the electromagnetic theory, and so we will not go into details how this relationship have been arrived at. But the point to note is that the probability of photoelectric effect is very dependent upon the Z. Higher the Z, higher the section for the photoelectric effect, and lower the energy, higher the probability for photoelectric effect. So if you, I have shown here is in as a function of energy of the photon, the cross section or the what you call as the attenuation coefficient for the photoelectric effect, it's coming down with energy. You can see here. So higher the energy, lower the probability of photoelectric effect. For a particular Z, for a particular atomic number, you can see here. So this is the K edge, this is the L edge, and so on. So what happens that in general, the cross section should come down with energy, but whenever there is the photon energy matches with the K shell binding energy, there is a jump in the cross section for photoelectric effect. Similarly, whenever the energy of the photon is equal close to the L shell binding energy, then there is a jump in the cross section. And so the cross section for photoelectric effect will have edges at the respective shell binding energies. So the photoelectric effect is one process that leads to complete deposition of the energy of the photon in the detector system. And so the typical spectrum, you can see here, what happens, suppose this is the counts versus energy of the gamma ray. Then if the energy of the photon was E0, then it will lead to a sharp peak. Ideally, it should be a delta function, sharp line, but the detector has its own resolution, and so it becomes a Gaussian peak. So there is a broadening in the peak of the gamma ray. So, but this is what, so there is no other effect of manifestation of the photoelectric effect in the gamma spectrum, except that suppose this is the IZ material, the detector is IZ material, so the X-rays are emitted and X-rays might escape detector. So there will be X-ray escape peaks. Particularly it happens in sodium iodide, which we will discuss subsequent lectures. The iodine is one of the components of sodium iodide, and the iodine X-ray might escape from the detector system, and so there will be a peak, full energy minus iodine K X-ray. That is called the iodine X-ray escape. Another process of the photon interaction is Compton scattering, and as the name itself implies, it is a scattering. So it is like an elastic scattering between the photon and the loosely bound electron. So here, the electron that is participating in Compton scattering is either a valence shell, almost loosely bound electron. So there is a collision between a photon comes, strikes the electron, and the photon is emitted at theta degree, required electron goes at phi. So it is like elastic scattering between the photon and the electron, and the energy of the incident photon is shared by the scattered photon and the required electron. So you can set up in fact, the equations for the conservation of energy and momentum of the photon before and after the collision. And then we will not go into it because this is a very simple derivation you can set up. So finally, we want to know what is the energy of the photon. That depends upon the angle at which the photon is emitted. And so the h nu dash, the energy of the Compton scattered photon, is given by h nu incident energy upon 1 plus h nu upon m0 c square. M0 c square, m0 is the rest mass of electron, c is the speed of light, and 1 to 1 minus cos theta. And so accordingly, the energy of the electron will be h nu minus h nu dash. So the energy of the incident photon is shared between the electron and the scattered photon. So the manifestation of this you will see in this, when we see what happens at cos theta equal to 0, when theta equal to 0, cos theta equal to 1, and then so this term becomes 0. So you have h nu dash equal to h nu. H nu dash equal to h nu. So that means at 0 degree, the photon goes undeflected. There is no electron energy is 0. When the photon is scattered at 0 degree. But when the photon is scattered at 180 degree, then cos theta is equal to minus 1. And you put here the value of cos minus 1 minus minus 1 become 2. So h nu dash is h nu upon 1 plus h nu upon 2 m0 c square. It should be 2 h nu upon m0 c square, 2 h nu upon m0 c square. So at 180 degree, this is the minimum value of the photon, scattered photon energy. Now let us do some simplification. If the gamma ray energy is much higher than the rest mass energy of the electron, m0 c square means 0.511 MeV, in that case, you can actually substitute this term, you can neglect. So it becomes h nu dash will be m0 c square by, because this will get cancelled with this. M0 c square will go in the numerator and it becomes m0 c square by 2. M0 c square is nothing but 0.511 MeV or 511 keV. Half of it will be 256 keV. So at 180 degree, if the gamma ray photon energy is very high, then you will find there is something called as a Compton edge, because the energy of the electron will be h nu minus 256. And so at a energy, full energy of the gamma ray minus 256, there is a peak. That's called the, it's not a peak, it's a hump. So that is called the Compton edge. So it is a typical feature of Compton scattering, which we will see in the subsequent slide. You can see here the Compton edge. This is so at this is 256. If the photon energy is much higher than the rest mass energy of electron, that is 511 keV. So you can see here, depending upon the scattering of the photon at 0 degree or 180 degree, you get a continuum in the gamma spectrum as a result of Compton scattering. This is the full energy. So Compton scattering does not lead to the full energy deposition. But what happens if your detector is very big in size? Then the Compton scattered photon can further undergo photoelectric effect or Compton scattering, and then you can have the full energy deposition, because even the Compton scattered here, it is assumed that the photon is scattered out of the system. But if the photon can further interact with the medium, then you can lead to full energy deposition. And the probability of the Compton scattering has a mild dependence on the Z and the energy of the photon. So here, what is shown here is the energy dependence of the photon. So as the energy of the gamma ray increases, the Compton scattering cross section decreases with the energy. But it is a very mild dependence. Now the third process is pair production. So essentially, in this process also, the photon is completely lost. The photon is absorbed in the Coulomb field of the nucleus, and the energy of the photon is used in producing a pair of electron and positron. So this process is seen schematically here, that the incident photon comes in the vicinity of the nucleus, and the energy of the photon is taken up by the nucleus, and instead of that, instead of the photon, it is like the inverse of the annihilation of the gamma ray, the pair annihilation of the positron with electron. So a pair of electron and positron is produced, and the energy of the photon is now going into the kinetic energy of the positron and electron. But to create a pair of electron and positron, you require the rest mass energy of the pair, that is 1.02 MeV. And so that is the threshold for this pair production process. The remaining energy, Hν minus 1.02, is going as the kinetic energy of the electron-positron pair. This positron will get thermalized in the medium, and it can meet another electron in the medium and annihilate the electron when it is thermalized to give you 2 511 keV gamma rays, which we discussed in the interaction of positron with matter. The net result of pair production, you can see here, you will have a high energy electron and 2 511 keV gamma rays. And then these 2 511 keV gamma rays can further interact with the medium. Either they can get deposited in the system, or they can get escape also. So if either there can be full energy deposition, the detector is large enough, or one of the 511 keV may escape. This is called single escape peak, or both the gamma ray, this 511 keV gamma ray photons may escape from detector. That is called the double escape peaks. So what you will have here, that from the, suppose this is the gamma ray, E gamma counts. So if this is the full energy, then you will find, and this is the Compton, this is the photo peak, you will see the single escape and double escape peaks on the gamma spectrum because of this 511, and this is 1.03, corresponding to single escape and double escape. So this is what happens there when the pair production takes place. So you can immediately make out that since the gamma energy is higher than 1.02, pair production will be dominant process. So the probability of pair production is varying with the energy of the gamma ray and the Z of the absorber in this fashion, Z square into ln of E gamma. Here the E dependence is shown, but there is a threshold for the pair production, and as you go on increasing the energy of the photon, the pair production probability increases. So at, let us say, 2 MeV, 3 MeV, you will find pair production will dominate the interaction of gamma rays with matter. So the net cross sections for all the processes, the photoelectric, The Compton scattering and the pair production are shown in this slide here. So you can see this is the photoelectric effect. You can see the K edge, and it is going down by after 1 MeV or so. Actually, this is for the sodium iodide, so it is impacting the sodium and iodine in the material. Then the Compton scattering, you can see here, Compton scattering. This is photoelectric effect. So it is coming down as 1 by E, and the pair production is going up beyond 1.02 MeV. The net result of these processes is the cross section for the whole process interaction will come down and then again start going up. So this is the way the gamma ray photons will interact with the medium, and when the gamma ray is traveling through a medium absorber, so how does the intensity of the gamma ray change with the thickness of the absorber material that I have tried to illustrate here? There's the incident gamma ray photon of intensity I0 is passing through a thin slab of the absorber material, and the transmitted intensity is I. Then the difference, the decrease in the intensity of the gamma ray minus di by dx, thickness, is proportional to I. Why this has come? Because in this case of gamma ray, where the gamma ray photon is interacting in one step, either it will undergo photoelectric effect or Compton scattering or pair production. In one event itself, the photon is removed from the initial flux, and so that process has got a, like, radioactive decay. Radioactive decay, atom decays, and so you have an exponential decay with time. In the case of this interaction of gamma ray, in one interaction itself, the photon is disappearing from its beam intensity, and so you have the similarly the first order rate law, and the solution of the differential equation is I equal to I0 e raised to minus mu x. That is what I have tried to show here, that the ratio of the transmitted to the incident intensity is exponentially decaying the thickness of the absorbing material. As the thickness is increasing, the gamma ray, the transmitted intensity is decreasing. And this, so you can see this mu you can get from here by fitting this equation, and that mu is the total. So we are not trying to break up them, but this mu, whatever we get, is sum of the three attenuation coefficient. The mu is called the attenuation coefficient. How does the gamma ray get attenuated? So mu photoelectric effect, mu Compton scattering, and mu pair production, the sum total of this is the total attenuation coefficient. Now see, the attenuation coefficient, we define two types of attenuation coefficient. One is the linear attenuation coefficient. Mind you, the quantity in exponential e raised to minus mu x. The mu x has to be dimensionless quantity. Anything in exponential is a dimensionless quantity. So if x is in thickness in centimeter, mu will be in centimeter inverse. So that is what is, this is, x is linear in thickness in centimeter. Mu is called the linear attenuation coefficient. But in the interaction, as I discussed earlier also, suppose you can have a 1 inch thick material with pores inside, and same thing you can compress, the thickness becomes 1 centimeter, but the density is different. So the density normalized thicknesses are called mass dependent thicknesses. And so that where the density independent mass attenuation coefficient can be obtained by dividing the linear attenuation coefficient by the density. So if you multiply this by, it is be rho, density of the material, mu by rho, so it will be centimeter inverse upon gram into centimeter cube. So this is the density 1 by rho, this is the mu. So it becomes mu m, that is centimeter square per gram. This is called the mass attenuation coefficient. So if you write the thickness in gram per centimeter square, so you multiply the thickness by density, x into density is centimeter into gram per centimeter cube. This is called the density dependent thickness. So normally in this interaction, so we will always talk about density dependent thicknesses, and so we have that. So that then this becomes independent of density of the material. So whatever value you get mu m, it is independent of the density. Whereas this attenuation coefficient linear one depends upon the density of the. Now I will just touch upon the interaction of neutrons with matter. Neutrons are also neutral particles. They are neutral particles, so they do not have any coulombic interaction with the material, but they will undergo scattering, elastic scattering, inelastic scattering, or nuclear reactions. And that is how we make use of these interactions to detect the neutrons. In the case of neutrons, so we can classify neutrons into slow neutrons or fast neutrons. In fact, there are other classifications like epithermal neutrons. I mean, there are some regions of energy of neutron where there are high resonances, like here I have shown here. The cross section for the neutron induced reactions fall as we increase the energy of neutron. In fact, this is called 1 by v law. Velocity of the neutron is increasing, so the cross section is decreasing. So thermal neutrons, the neutrons of low energy, are more reactive than high energy, and somewhere in the middle, around 1 to 2 1 electron volt or so, there are resonances in the cross sections. There are whenever the nucleus is matching with its energy, excitation energy. So what we want to show is that thermal neutrons are more reactive, and so many times to detect neutrons, we need to thermalize the neutrons. So we will discuss the interaction of slow neutrons and fast neutrons a little bit separately. Slow neutrons are highly reactive. And why it is called cadmium cutoff? The energy of neutron less than 0.5 electron volt is called cadmium cutoff, because at 0.5 electron volt, cadmium has got this kind of resonances. And so if you put cadmium, the gamma rays are, the neutrons are totally absorbed by this cadmium. So that's called the cadmium cutoff. Means the energy which is absorbed by the cadmium. So if you wrap a sample by cadmium, then low energy neutrons are all absorbed by the cadmium. You will see only the fast neutrons. So the thermal neutrons, though it will undergo elastic scattering, but that is not important from the point of view of detecting the neutrons. The slow neutrons will predominantly undergo nuclear reactions. It can be neutron capture and gamma. It can be neutron-induced reaction, proton emission, followed by preceded by neutron capture, N alpha, or fission, neutron-induced fission. So you can see detectors based on boron, BF3 gas, where boron 10 interacts with the neutron to give alpha and lithium 7. So these are the charged particles, and they will be depositing energy in the medium. Similarly, helium 3 gas, NP reaction, tritium. So the tritium and proton, they are the charged particles. Similarly, the 235 uranium, neutron-induced fission, the fission fragments are charged. So the net result of the nuclear reactions by neutrons with different detector materials will be the production of charged particles, which will interact with the like heavy charged particles and deposit their energy in the substance. The fast neutrons can also undergo inelastic collisions apart from elastic collisions, and they can excite the nuclei, or they can undergo nuclear reactions. So when it is undergoing elastic scattering, we have recoil nuclei, like a neutron can interact with the proton and knock it off from the place. So we can have the heavy charged particles as a recoil nuclei, or the fast neutrons can also undergo nuclear reactions like NP, N alpha, NF, neutron diffusion, and N2N types of reactions. So this neutrons detection can be done using the nuclear reaction. In fact, mostly the neutrons are detected using the nuclear reactions. And what is the range that neutron, how much distance they can travel, like they are neutral particles. So the energy loss mechanism is first initially only by elastic scattering or inelastic scattering. So if a neutron is colliding with a nucleus of mass number A, atomic number Z, then it can just give a kinematics you can set up, and like we did in the case of heavy charged particles and electrons, the energy received by the recoil nucleus will be 4mm upon m plus m square into energy of the incident neutron. This is the same formula we derived for the heavy charged particles. So same thing applies here. Now let us assume that for protons, so protons and neutrons are relatively same mass. So m equal to small m equal to 1. And so if you put the value here, then you will find the energy of the recoil will be energy of the neutron. So that means what? With the proton, when the neutron is interacting, neutron can give all energy in one single collision. Like in the case of fast electrons could give all energy in one collision. So when you want to reduce the energy of neutron using a moderator, the proton or the hydrogen material is the best moderator. So then that is why you will find water is used as a moderator in the reactors. There are other problems with the water, so we use heavy water. Now, finally, the cross sections. This is called the microscopic cross section. When a neutron is interacting with the nucleus, we call cross section as sigma. But when a neutron beam is passing through a material, we call capital sigma. It's called macroscopic, where n is the density, nuclear density. So nuclei per cc, number of nuclei per cc, or number of atoms also you can say per cc in the material. And so the sigma actually is like, decay constant of a neutron. Like when we have the beam attenuation of the neutron, you can see here that when neutron beam is going, then I0 to I, the neutrons also will follow the similar type of expression, I equal to I0 raised to minus sigma x, where this sigma is the microscopic cross section. And many times we associate a mean free path. That means what is the distance traveled by the neutron without interacting the material? That is 1 over sigma. So these are in fact used in the reactor physics when the neutron economy is being discussed, how the neutron is diffusing in the reactor system. These concepts become important in that. So I'll stop here and subsequently discuss the detection of radiations by different means. Thank you.